early spanning tree in regards to root bridge placement. There's a lot of good info out there about spanning tree already in the form of videos and blog posts and vendor documentation, to where I don't really feel like I need to go through all the basics. But for your reference, some things you would need to know beforehand before this probably makes more sense. You need to know the basics of the spanning tree protocol. You need to know how root bridge actual selection is done. In other words, how that election happens and who becomes the root bridge. And finally, you need to know how that actual path to the root bridge is put in place to where it's loop free, because that spanning tree is designed to do nothing more than give you a loop free topology. Because from a layer 2 perspective, there is no mechanism to prevent infinite loops like there is with, say, layer 3 IP. You have a TTL, a time to live, which decrements as it hits each hop, and eventually, when that hits 0, that traffic gets dropped. There is no mechanism like that from a layer 2 perspective, and so that's where spanning tree comes into play. Because again, if you hook up two switches to each other with multiple links, very easy to overrun both of those switches and turn the lights out in the room, and you can see all the actual ports light up. Pretty interesting exercise. But those are three things. I'll put some links in the actual video and on my blog site where I actually post this, so you have links to watch those if you need those. All right, so from a spanning tree perspective, classrooms, labs, those kind of environments, you typically see basic setups like this, like number one, where maybe you have like two core, two distribution aggregation switches feeding some other switches, and it works the same even if we were to add a third switch or what have you. That's the root. When you start setting up the actual loop-free path, everything's gonna go through the actual root to move around to the other switches. This guy right here, even simpler. Everything is going to go through the root. So if I am at switch 1 and want to go to switch 2, that's pretty much my only path. Because even if I had a path here, it's going to end up getting blocked. Let's just say for the purposes of this illustration, it'll get blocked. And so you are going to traverse the root. So not uncommon to see that in a purely academic environment. The real world's a little bit different. You'll get out there and you'll see on networks things like this, where all these boxes represent switches, and maybe you've got a core 1, core 2, or aggregation 1, aggregation 2, doesn't really matter. And the root has actually been set on core 1. Now, if you're doing per VLAN spanning tree, where there's a different instance for each VLAN, logically it would look the same as this. It doesn't really matter whether we're talking common or whether we're talking for individual VLANs. Root bridge placement is still very important. So let's say we come across a network setup like this with these kind of physical links. Again, this happens in the real world. Right? Money concerns, maybe there were cabling issues where I couldn't get switches down here up to here. Maybe I didn't have the proper optics because it was a long haul and the switch only supports copper. Any number of reasons, or just maybe the person that set it up wasn't really thinking about that, and they got lucky. Let's say they were using default values, and this guy just happened to be the actual root. This does happen out there. All right, so using that same example, this guy's the root. What happens if another switch gets spun up over here and gets connected to this guy, and he happens to have a more preferable MAC address? He's using the same 32.768 priority as this guy, or maybe someone came in and said, "Oh, I'm going to set the priority to 4096 for whatever reason." Maybe it was an older switch. Any number of reasons, right? And so core 1 no longer is no longer the root. Now I've got this other switch sitting out here. This become the root. So what effect would that have on the actual traffic? Okay, so here we have the same network, and just for the purposes of brevity, I've gone ahead and just made it loop-free in terms of a single path getting to the actual root bridge. So now that I'm here is my root bridge, and my path logically looks like this, where the other links have actually been previous page. You can see where there are multiple links all over the place, or at least from the first two layers. Realistically, it's going to look like this logically. Again, common spanning tree, per VLAN spanning tree, doesn't really matter. Each instance is going to have its own topology, but let's say it looks like this. All right, so let me change colors here. So let's say I've got a PC down here, and I'm connected to this switch right here, and I want to talk to a server that's hanging off of core 1. All right, so now that I have this topology in place with this root bridge being over here, I'm going to take a path that looks kind of like this. I'm going to go up into core 2, I'm going to come down into here, and then I'm going to go all the way over to here and come out this way. I'm not going to actually go up to the root bridge. I mean, the MAC addresses are being learned, so as far as the destination goes, as long as this switch right here knows that the MAC address for this server resides on this port, then, resides here, I'm going to go out that way and go up there. So this is definitely a suboptimal path. With other links that were in place, it would have been simpler if I could have gone from this switch right here up to core 1 and used that link, except it's blocked. It's not actually forwarding traffic due to spanning tree doing its thing and finding a loop-free path up to the root bridge. So just a quick example of how that could actually happen. It does happen, and it can affect your traffic. Depending on the application, depending on a number of things, you might not really even notice. It might be that you get under a tremendous amount of load, and then you start to see some latency in that actual connection. There are times in which things like this happen where no one really notices because the load isn't enough, or there isn't enough latency to where you can really tell. But it is not the best way to get there, and it is kind of a poor design if you allow some switch out there to just become root at will. I'll give you an example of a network that I dealt with at some point during this year where they had just a single core switch, and they had a few other switches out here. And this guy over here, let's say this is the core, this guy over here was the actual root. Well, it didn't really affect anything because everyone's connected to the core and everyone had an actual link active on the core. And so from a layer 2, from a MAC learning perspective, if I was off of this switch on a PC and needed to talk to a PC over here, I'm coming up through the core already and coming straight back down there. So that wasn't a problem. There are these cases where you do have a root bridge that's sitting off in a closet somewhere that isn't optimal, but if you're dealing with something like a single core switch, it's not really a big deal because I'm having to come through the core for everything anyway, so I never really noticed the problem. But again, if we deal with an environment like this, it is a problem, and it quite possibly will be noticed in the form of latency. So just wanted to give a real quick video about root bridge placement and why it's important. Again, we know what the root bridge is, we know what its purpose is, we know that we build a loop-free path to it, but we don't always get examples or have people talk about why that root bridge needs to reside kind of at the top level of your layer 2 network where everything's kind of aggregated. It has to, again, because of things like this suboptimal paths.